What's up everybody, thanks for joining this video, and today we're going to be looking at designing data-intensive applications. So we're going to be continuing the series that I started like 2 weeks ago, and today we're going to be covering chapter 3, which is about storage and retrieval. So in this chapter it covers all things related to indexing, so we're going to look at different data structures that do indexing, so for example a hash table, an SS table, or a B tree, and we're going to be looking at these things using animations and graphics that I made. So I've been using this new framework called Motion Canvas, and that makes some really beautiful animations. So I hope that you guys will enjoy this video because I spent a bunch of time making it. So let's start. A database, at the very least, regardless of whether it is a relational database like Postgres or MySQL, or a NoSQL database like Mongo or Redis, needs to be able to do two things: store data and retrieve data. Chapter 3 covers exactly this, and it looks at two storage engines that are capable of performing storage and retrieval efficiently. Achieving a high write throughput is quite easy. Imagine we have a file that stores any new incoming data at the end of the file. That would be a database with high write speeds because appending to a file is quite a fast operation. However, as the file would grow with keys in random order, it would become increasingly hard to find the value of a particular key. In algorithmic terms, the cost of a lookup would be O(n), as you'd have to scan the database beginning to end, searching for the key of interest. This is where an index comes to the rescue. An index is an additional structure that helps you locate the data you want. Indexes don't affect the contents of the database, they only affect the performance of queries. This index is called a hash index, and it keeps a hash map in memory that stores the byte offset for every key in the database. For example, if you need to find out if the user keylang is a dog or not, you would simply check the hash map for the key dog and read from the file at the specified byte offset. This is a simple indexing approach and has several downsides. For example, if the database crashes, then our in-memory hash table will be erased and needs to be created by reading the contents of the database again. Most of all, the hash table needs to fit in memory, so if you have a very large number of keys, you're out of luck. Let's take a look at how we can improve on the hash table approach by using a format called sorted string table. As the name suggests, the key of the table are in sorted order, and this means that you no longer need to keep an index of all the keys in memory. In this example, the key hammock references a value way earlier in the file. The key handbag references the first value of the segment on screen, the key handsome references a value later in the segment, and hangout references a value way later in the file. We can now easily find any key between these four key values. Say you're looking for the key handiwork, but you don't know the exact offset of that key. However, you do know the key offsets for handbag and handsome, and because of the sorting order, you know that handiwork must appear between those two. You still need an in-memory index to tell you the offset of some keys, but it can be sparse, saving a bunch of space. Sorted string indexes are gaining acceptance, but they are not the most common type of index. The most widely used indexing structure is quite different, the B tree. What I found interesting is their dominance as indexes. They were introduced in 1970 and called ubiquitous less than 10 years later. They have stood the test of time very well and are the standard index implementation in almost all relational databases, and many non-relational databases use them too. B trees share only one thing in common with SSTables. They sort key value pairs by their key. B trees have a very different design philosophy. They break down the database into fixed size blocks or pages, usually 4 kilobytes in size, and read or write to one page at a time. Each page can be identified using an address, which allows one page to refer to another, similar to a pointer but on disk instead of in memory. We can use these page references to construct a tree of pages. One page is designated as the root of the B tree, and whenever you want to look up a key in the index, you start here. The page contains keys and references. Each child contains a continuous range of keys, and the keys between the references indicate where the boundaries between those ranges lie. So this references a page containing only key ranges between 100 and 200. So let's quickly look at an example of finding the user with user ID 251. We start at the root page and look at the reference between 200 and 300. That takes us to our first child page that further breaks down the range. So we take the reference between 250 and 270. Eventually we get down to a leaf page, which contains the value for each key, or contains another reference to the page where the values can be found. There are algorithms that can keep this tree balanced, ensuring that all basic operations, such as insertion and searching, are done in O log n time. Alright, so that's the animation. I hope you guys enjoyed it, and I hope it was useful because it took me a long ass time to make. So yeah, I tried to cover the most important things of chapter 3 and also the things that I found the most interesting. So that was mainly basically the indexing and data structures behind those indexing. So yeah, the storage engines and stuff like that. But yeah, this is one of the longest chapters in the book, so it's kind of hard to summarize all of that. The book talks a lot about other things, such as the performance optimization of each indexing structure, so of B trees or of LSM trees. It also goes further into depth about the comparison, so comparing B trees and LSM trees, and when you would want to use which indexing structure. It also talks about different indexing structures. So we only covered key value pairs, but you can have different indexing structures that are, for example, secondary indexes that rely on multiple columns in the database, stuff like that. And there's actually this whole section about whether your database is for transaction processing or analytics. So if you have an analytical database, then you probably have way more data, and then there's a whole different kind of setup that you can use. But for most indie developers and for most developers, they won't be using this kind of analytics-based database. So I decided to kind of skip that part because I also found it less interesting. So keep in mind that this is just a biased summary of chapter 3 of what I found interesting and the things that I think that you will actually come across and use in your development experience. So thank you guys so much for watching this video. I really appreciate if you made it to the end. And if you did, please leave a like, leave a comment, and subscribe to the channel. Honestly, the thing I would prefer the most is a comment, just to hear what you guys thought of it. That's always what I find the most interesting, and just to start a conversation. So thank you guys.